Hello everybody, welcome to Distributed SQL 2020. This is Hale Donertasli speaking. I am working as cloud architect at Rakuten. Today I will be presenting 5G and data challenges. So 5G demands full capacity and availability of data delivery, while living in a decade that all layers of connectivity are going through the massive partitioning. We are going to discuss the strategies to deal with data challenges for 5G. Let's move to the agenda. So first, I will be talking about data in 5G service-based architecture. And then later, we will be discussing 5G data challenges. And I will conclude the presentation by introducing 5G database common interface. The first topic, data in 5G service-based architecture. Data is stored in UDR and UDSF in 5G, and we will be discussing what is new in 5G in terms of data. In this slide, we see evolution of mobile network generations. As you can see, data rate is increasing and hitting 20 Gbps for 5G. So one of the main differences between 5G and previous generations lies in 5G's strong focus on machine-type communication and the Internet of Things. This paves the way for the next era in industrial production, known as Industry 4.0, which will be receiving the most data from. As you can see in this picture, 5G will expand mobile ecosystem. Imagine you have a health condition that urgently requires surgery, but it can only be performed by a few specialist doctors who are based near you. Or picture yourself taking a ride in a self-driving vehicle which effortlessly navigates busy streets. More simply, you can probably see yourself downloading a movie to watch. What if that only took a few seconds? All these things and many more could become our day-to-day reality with the power of 5G. It is predicted that the connectivity of 5G technology changes everything from our health and well-being to transport and manufacturing processes. All this revolution happens due to 5G service-based architecture. So as you can see here, there are network functions defined by 3GPP in service-based architecture, and they have access to each other's services. If we look at the data storage in 4G and 5G, we see UDR and UDSF. The subscription-specific data are stored in UDR. UDR stores the data in a structured format, and the data is shared with other network functions. The required session or state data of the network functions are stored in UDSF. This data is network function and manufacturer specific. In this picture, we see 5G core functions and their relations. As you can see, network functions connected with each other, specific interfaces. Each network function service exposes its functionality through a service-based interface. The UDM provides services to other functions, such as the AMF for mobility, SMF for session management, and NEV. UDM is typically recognized as a stateful message store, holding information in local memory. UDM, however, may also be stateless, storing information externally within UDR. Looking at data functions in 4G and 5G, we see UDSF is connected to AMF, SMF, and other network functions. And 5G UDR is connected to NEV, PCF, and UDM. 4G UDR is connected to HSS, AAA, and PCRF. So looking at here, UDSF is new 5G database, and it must meet tough requirements, such as carrier-grade 5 nines availability, data access latency of less than 1 millisecond, ability to scale for very high throughput and massive workloads, ability to handle massive continuous updates, processing power for massive create and delete operations on user context information. So the next topic is 5G data challenges. We will be talking about consistency, availability, and partitioning, and how to keep balance on those three. 5G data challenges, number one, response time. So if you look at in this picture, you will be seeing different response times expected from different domains. Network processing and data access generally require response times below 1 millisecond per request. Data access times and allowable latency also vary for human operations and service domains as shown in this picture. When the actual latency targets for data access are designed to meet the response times for each of the applications listed in this picture, it is important to note that less than 50 microseconds per data input-output operation is needed to assure 1 to 2 milliseconds per completed access. So this is the second challenge, the transaction per hour. In this picture, you will be seeing a 4G function HSS compared to 5G function AMF. So they are similar network functions. Not only are the data functions different in 5G SPA, but the number of TPH required can easily be 1 or 2 orders of magnitude greater prior to optimization. For example, looking at 5G AMF TPH with the traditional HSS for the same number of subscribers. SSS TPH was around 5 to 10 TPH, and at the same time AMF required, like it can be over 100, and optimization at this time becomes essential. Number 3 challenge is throughput falls. So as you can see from the picture, storage of very large objects reduces throughput in and out of the databases. So operators must be very careful about exactly how objects are stored and retrieved to avoid huge databases. Those are costly and slow to respond, so they are creating bottleneck for service delivery. The other challenge is flexibility in stateful approach. So stateless is the way to cope with availability issues, and it is a sensitive topic because all functions are depending on each other directly or indirectly. There is too much flexibility around stateless approach, and this leads into interoperability problems between data consumed by network functions. I'll give you an example. So consider your system 70% of stateless and 30% of stateful. That means your whole system is stateful because you're adding stateful in it. So I want to give you an example from 3GPP. Let's read this. It is up to the network function implementation to determine whether the storage entity is used as primary storage or the storage entity is used as a secondary storage. So as you can see from here, there is a lot of flexibility to pick the storage as stateful or stateless. So of course, when there is a lot of flexibility, there is thousands of ways to implement something, right? So then here comes interoperability issues. And number 5 challenge is data inconsistency and race conditions. So in the volume of 5G data, it is very possible to run into race conditions, and these are directly from 3GPP. So let's read them. If one of the network function group consists of multiple sets and instances from different sets may be selected to serve the same UE, user equipment. The temporary data which is not shared across different sets may be lost. The event subscriptions stored at one UDM instance are lost if another UDM instance from different set is selected, and no data shared across the UDM sets. So in the next slides, we will be introducing a new project, and there we will cover these race conditions. And the second one is multiple network function service instances may require to access to the same stored data in the storage entity around the same time, and then the resolution, the race condition is implementation specific. Again, in the introduced project, in the next slides, our goal is to cover those race conditions by testing and introducing all the network functions in this race condition and preventing them. Okay, we have talked about the challenges, and now let's talk about the solutions for those challenges. Most important one, protect from the repeating patterns of partitioning. So let's go through this circling picture quickly. So when we have a new hardware innovation, we tend to go back to the monolith, because monoliths are the solid piece of software or hardware works very well. You don't need to worry about how to partition it and then extra layers to make those partitions to talk to each other. And after hitting that, we go beyond the supported scalability, supported capacity. And then until the next new hardware innovation, we run into massive partitioning again. So right now we are right here. This is happening now in all kinds of industries until we see another new hardware innovation, like a cheaper memory, cheaper cache, you call it. So looking at this picture, time repeats itself. We are going through the massive partitioning until the new innovation happens. So during this time, I totally get the advantage of partitioning, but having 100 partition, 100 granularity is not any better than 10. So we need to keep this partitioning, like granularity of microservices, as minimum as possible. And here is why. Because we want to keep balance in CAP theorem. What is this CAP theorem? As many of you already know, it is the pick two from availability, consistency, and partition. You can't deliver all three at the same time. But in the current situation, we already picked P, which is we are on massive partitioning. So now how do you deliver consistency and availability? And it is needed because 5G is 5.9 requirement. Well, in that case, we need to define new standards if standard development organizations standards are lacking on that. Yes, we need to define the standards when things are contradicting. So let's look at this contradicting things. Microservices require dedicated single ownership of schema and underlying data store. And watch how it is contradicting the next things. UDSF microservices share a container or have a container on the same backplane with the network function services in order to transfer data in microseconds. So databases and data stores should themselves be stateful services. And the content and format encoding of operator-specific data are not subject to standardization. The organization of different data stored in the UDR is not to be standardized. So I see a huge contradiction in here, which prevents transfer data in microseconds. So then just define your own standard. Have your common database and rule your data, own it. So standard development organizations have their own challenges. It is really, I understand them, it's really hard to keep everybody happy until everybody agrees, and now they have a really nice standard. It is already old technology. We're already moving on to new technology, but until they had a really solid standard. So define your own standards. Until now, who has done what is, okay, 3GPP defined standards, they are valuable, but again, there's 1,000 ways to develop them, implement them. That flexibility even creates some interoperability issues. That's where we define our own standards. We see a bunch of commercial products in here. I'm sorry if I missed any of them, but they are missing something for us. It's telco's cost saving and practical perspective. And connected to 5G standards, but not enough depth to reality of it. And they are creating vendor independent architecture, of course. And I don't see clear 5G data translation between different operators. Just search for 5G data schema. You won't really find much. Hybrid approach for room to evolve, in-house, test and try. Flexibility to plug and play new open source solutions. I don't see that. And cap balance. That's very important, and we just reviewed it, why it is important. Now it is time to introducing 5G database common interface. Rakuten Yugabyte collaboration. It is about DB specification for 5G's ultra reliability requirement. Let's go through the 5G DBCI features. Feature number 1. Data interoperability for 5G functions. This is the first thing must have. And let's review them. I'm excited about this project. The first thing is, okay, so there are a lot of high-level standards defined by 3GPP and ETSI. But we need to define low-level standards because, right, we need to implement it or we need to test it, whatever. So first low-level standards are 5G core functions and OSS data on that. UDR and UDSF database schema, there are a lot of structured and unstructured. Let's see if there is any way to make unstructured data more structured. And service-based interface requirements. This is for 5G core functions talk to database, and again OSS to talk to database. Keep cap balance. I keep saying this is very important. So I know software engineers are very excited about making microservices very granular, but we have to keep eye on it because it is eating up from the resources of consistency and availability. And I'm coming from actually a test engineering background in my first 3 years at Google. So to prove something is working, we have to test it in every level. 5G latency tests so that we can deliver the response time less than 1 millisecond. It has to be strongly consistent, zero downtime scaling, geo-distributed for HIL resilience, and it has to be self-healing. So if you look at this in an agile manner, defining low-level standards, SPI requirements, and keeping balance in cap and running through the tests. If tests fail, we're going to maybe define the SPI requirements or low-level standards, or we need to make the microservices less granular. So this is like a circle that we can have data interoperability and prove that it's working for the 5G latency requirement. This is the second feature. service logic for 5G core functions is very important because this is where the core functions talk to the database. You see here yugabyteDB, and you can see the stateful and stateless layers. So 5G's ultra reliability requires the coupling of network functions into data and compute. And in this picture, you see it is already separated. So this results moving dedicated databases to the common database, in which is yugabyteDB in this case. And 5G DBCI is formed to create service-based interface expectations from network functions for them to work together in harmony. So, as you can see from the picture, 5G DBCI defines the practical database schema and service logic for both OSS and network function databases, which is UDSF and SDSF. And it is going to include UDR as well. This is one of the most important features. It is a distributed SQL approach for 5G core functions. Thanks to Yugabyte for providing this feature for Rakuten. And let's look at the picture. And you see distributed 5G core functions in this picture. You see this network slices. So 5G comes with a huge bandwidth. So we need to slice it up for different applications. So you see phone slice, URLLC slice, EMBB slice, and rest of it. So, and if you look at in each slice, some of the core functions are more shifted to the edge for the small response time. And this is possible by having a database which can support distributed SQL, as you can see in Yugabyte's DB case in the picture on right-hand side. So in the past Gs like 4G or 3G, all services were delivered from the core and all of them had the same latency, let's say 50 milliseconds. So in 5G, there are services in like ultra reliable low latency communication category where the requirements is less than 1 millisecond. And there we need to move the core network functions closer to the edge, closer to the user. In 5G, network functions are distributed across core, edge, and far edge data centers, depending upon the service requirements. So a user plane function for URLLC service may be located in the far edge, while for broadband or voice services may be located at the edge or core. So this put forward the requirement for a distributed SQL. Instead, all of the queries go into a central location, and that comes with the attached delay. So with the distributed SQL approach, we are avoiding that attached delay so that we can meet 5G latency requirements. So thank you all for listening. You see my background in this intro. I am coming from SDN background, which is more in infrastructure layer, but I care about data a lot because this is what we need to steer in the bottom in the infrastructure layer, since it is now data-driven technology. So take care of yourself.